Right, line A5, learning task 5. Today we're going to take a look at calculating the neutral current inside of a Y-connected circuit. And this is something that's going to be exclusive to Y-connected circuits because the delta, we saw that we have no neutral connection, we have no ground or anything like that that we can tie to on a regular delta system. There are a couple of oddities, corner grounded delta, and then that 4-wire delta that we looked at before, but those are rare. By and large, we're going to mostly be dealing with Y-connected circuits. So it's important that we figure out how to calculate the neutral current, how it adds, and how it subtracts from itself. Using a neutral in these Y-connected systems is huge for us. First of all, the first bullet point in the learning task over here, 3-phase 4-wire circuit can supply both 3-phase loads, motors, etc., as well as single-phase loads, lighting, plugs, etc., between the line and the neutral. The neutral conductor is just going to carry any current imbalance back to the source. And we have to understand that what we have with electricity is that the electrons are always trying to get back to the source transformer. So if we've got a single phase load, it's going to get delivered along the hot line, and then they're going to go and return back along that neutral, etc. The other point that they have here is that the neutral is a convenient point for grounding the system, which improves safety. The neutral is convenient for that. The neutral is going to be grounded, but more than that, it does this thing that we are going to go and call stabilization. It is going to go and, let me just write that out. It is going to go and make sure that our voltages across our loads are going to go and stay locked down. They're going to be constant. They're not going to be jumping all over the place anytime that we get changes on the system itself. And so that is a really, really big reason why we use these neutral systems. Let's take a look at the actual calculations for the neutral. First diagram over here is a 3-phase 4-wire lighting circuit that we have, and we see that there are going to be a whole pile of currents that are going to be entering over here. We're just going to go and draw those currents. We've got A current, we've got the B current, and we have got the C current that are all going to be entering along their lines. And we know that according to Kirchhoff's law of currents, anytime that we have current entering a node, there's the node in the center, the sum of all of those currents has to go and leave that node as well. So we're going to go and have a neutral current that is going to come back out of that central over there. The big thing with adding these currents up is that they are now going to be added at phase angles. To take a look at them, because it's a 3-phase system, they're each going to be 120 degrees apart. And what that really means for us is if we've got equal values of current, if IA, IB, and IC are the same size, that we should be able to go and close off a triangle, add all 3 of these together, and be able to go and form a closed triangle. Take a look at IA over here. If I take IA, and then I'm going to go and add my next vector over here, which is going to be my IB. I'm going to add them tip to tail. And then I'm going to go and take my last vector, which is going to be IC. Oh, sorry, I did the wrong color here. IB down here, and then IC going up here, red, black, blue. We see that ultimately we come back to the exact same point that we started, which is going to be a point of 0. So if I've got all 3 of these neutral currents that are going to be the same, I'm going to end up with a value of 0 actual current, which sounds pretty funky. We see these diagrams, it's a 60 degree, it's an isosceles triangle that we are going to go and have over here. Or is it equilateral? I can't remember. Maybe just disregard that whole thing because I can't remember what the triangles are. But it's one of those equal, equal, equal type of triangles that we are going to go and have. Let's do some of these calculations now with some math. Over here, we have got a system. It's a Y-connected system. It's a 120/208 volt. Now, we haven't talked about slash ratings yet, but slash ratings are going to go and tell us simultaneously both the phase and the line value of voltage. So if I've got a 120/208, that means that line to line, I'm going to go and measure 208 from A to C, and that if I were to go and measure from any one of my lines to neutral, we'll go from A to neutral over here, I would get a value of 120 volts. This means that I can just take these values and I can parachute them right into my drawing over here. This 120 volts gets placed across every single one of these resistors over here. So let's just quickly do that. We'll put in 120 volts on top of each of these. 120 volts, 120 volts, and 120 volts over here. Now that we know what our phase value of voltage is, that's voltage phase, my phase value of resistance is, I should be able to figure out the last thing that I'm missing, which is going to be my I phase, the current that I'm going to go and have on that phase. So I'm going to go and do Ohm's law for that. I is equal to E phase over top of R phase. The phase values, we'll just put in the E phase as being that full 120. And I'll put in the R phase as being that 10 ohms over there, which tells me that my I phase is going to be 120 divided by 10, which gets me to a value of 12 amperes. Excellent. Well, if I have got 12 amps flowing through here, I'm going to go and have 12 amps coming through the line because it's a Y type of system. I'm also going to go and have, because it's the exact same values, 12 amps here, and I'm going to go and have 12 amps over here. And so what we can do now is we can go and add these up. Well, the first thing that we're going to do is we're going to recognize the fact that these are constantly rotating. Remember, we talked about phasors, vectors, and scalars. They're phasor values, which means that they're constantly rotating around, but we're going to freeze them in time. We're going to pick one of them as being our reference. We're actually going to go and pick the A line as being our reference, just because I prefer that one. And so we're going to say that A, if I would freeze time, I would be able to go and take this whole circle, or this whole delta that's constantly rotating. I'm going to freeze it so that my A is going to be at 0 degrees. I'm going to go and have my B that is going to be at negative 120. Remember that it is lagging the A, so it's going below into the negative Y. And I'm going to go and have my C that would be lagging the 120, or lagging the B phase if I take a look at it, but I could also say that it's leading the A phase like that. And that's where those three are. And so I could just go and take those values and punch them into my calculator. We're just going to put this on 120 angle 120. This one is going to go and be 120 angle 0, and then this one over here is going to be 120, and then you can go and do this one two ways. You can either do it as a negative angle, or you can do it as a positive angle. If you do it as a positive angle, it's going to be 240. It's 120 minus out of 360. You can do either one. I prefer to just keep everything positive so that I don't end up dropping any numbers on my calculator. We're just going to add all three of these together. Oh, and sorry, I'm making a mistake over here. I'm looking at the voltages. What we wanted to be talking about was we want to be talking about the currents. So we'll just replace those with the current values. 12 at angle 0, 12 amps at angle 120, and 12 amps at angle 240, like that. My apologies. Sometimes it's really hard to talk and draw and write all at the same time. Okay, so I've got my calculator back in polar mode over here, and I'm just going to go and add these up. 12 angle 0, that's my A phase, plus, because they're all entering that same node, so I'm going to add them together. 12 angle 120 plus, because they're once again entering that same node, so adding them together, 12 angle 240, and then I hit equals, and I see that my net amount of current is going to go and be 0. And if I go second function to my degrees, there's nothing for it to show me. There's 0 degrees. There's nothing that's actually happening. It's 0 magnitude at 0 degrees. In other words, all of our current has canceled itself out. It's pretty fantastic. It also saves us a whole page and a half of math that they have with trig over there, where they're trying to do it through sine and cosine and things like that. We're just going to go and forget about doing it in the J operators, and we're doing it like this with our polar format. What's beautiful about this is if I take a look at this, I see that I'm delivering full value of current along this line, along this line, along this line over here, but my actual neutral itself is carrying back 0 amps. At this point, it is carrying back 0 amps. So if I've got a balanced load, something that is going to be three-phase load that has the exact same values of resistance across it, I'm going to have 0 on my neutral. The code book is actually going to give us places where we're allowed to derate the neutral off of that fact, knowing that we've got less current coming back from the neutral than what we have coming in the lines. And this can really save a lot of time and effort when you're doing pulls on large feeders and things like that. Okay, let's try one now where our currents are going to be unbalanced, because this was a balanced system and we came out to 0. Now let's try one where we have got differing values of current. Over here, they're not showing us the resistances, they're not showing us the voltages, they're just showing us what the currents are in each of my three lines. If I take a look at my A line, it's 12 amps, and if I wanted to, I could go and place an angle off of that one at angle 0. It's my reference. If I take a look at my C line, it's 6 amps, and I can go and place an angle off of that one of 120. And if I take a look at my B line, it's 10 amps, and I can place that one at its angle of negative 120, or we're going to go with 240 at this point. So these are the values that I'm going to go and add together. 12, angle 0, 6 at 120, 10 at 240. If I add these three numbers together straight up, I'm not going to get anything mathematical. They have to go in with the angles attached, because otherwise you're not going to know whether they're canceling out or not. Okay, let's go to our calculator over here. I'm going to clear that. First number that I had, my A phase 12, angle 0, that I'm going to go and place in. Next one that I'm going to go and add, because we're looking for what we'd have for neutral current coming out of this, is going to be my B phase, which is going to be 10, angle 240, plus, we're going to add in my C phase, 6, angle 120. And we're going to hit equals, and it tells us that we have got a magnitude of 5.29 amps, so that's our total amount of current, and that the current is coming back along a angle of negative 40.9. Now the negative 40.9 doesn't mean anything. We don't need to graph it, we don't need to draw it or anything like that. We could draw it onto this other vector that we have, and maybe we will here in a second. But it is telling us that it's just out of phase with everything else. This current is not in phase with the A, which is at 0. It's not in phase with the B, which is at 240. It's not in phase with the C, which is at 120. It is just out of phase current that we have, and it's a magnitude. So let's go back to the first value, 5.29 that we have. That means that for all of the current that we have together over here, our neutral current is going to be 5.29. It's roughly going to end up right about there, 5.29 at angle negative 40, or you could go and call that thing 320 degrees, whichever one you want to go and have. What's really cool about this is if we take a look at it, we can also draw this one out, once again, just taking the vectors and adding them tip to tail. I'm going to just do that. I'm going to go and scale this. So I've got my 12 amps over here. Then I'm going to go and add my B phase onto that one, which is going to go and be 10 amps going down over there. And then I'm going to go and add my C phase, which is going to be 6 amps going back up. And you can see the point that we end up with is roughly the same thing. Now, obviously, I'm freehand drawing these, so my angles and my lengths and stuff like that aren't quite perfect, but you get the point that this thing is going to go and end up at a value that's going to be right about where we drew it out. The other issue that we have is actually some of the vectors that are inside of here. If you take a look at this one, this is supposed to be 10 amps, and this is supposed to be 6 amps. You can see that the 6 amp one is actually longer than the 10 amp. It was just poorly drawn by the original artist inside of here. It doesn't matter much as long as we get the idea that we can either go and take them and add them in polar format, 6 at 120, 12 at 0, 10 at 240 to get the value, or that I could go and do what I just did over here where I went tip to tail and ended back over there. The tip to tail, though, is going to require you to be very accurate in your measurement, your scaling, and use of protractor, etc. I don't suggest it. It's just a proof inside of there. Okay, so when we have unbalanced load, what we're really getting out of this one over here is unbalanced equals neutral current. Neutral amps that we're going to go and have. Anytime that the load's unbalanced, whatever we've got for the unbalanced current, in this case it's going to be that 5.29 amps over there, is going to go and come back along our neutral. Okay, that's kind of cool. We can see that, now we cannot just take the neutral out. When we looked at the very first one where we had a balanced load, we saw that we had 0 amps, and some of you were probably like, well, just get rid of the neutral then. What's the point of having that sucker in there if it's not doing anything? Well, we do need it because if our loads become unbalanced, all of a sudden it's going to become critical that we've got a place for that to come back along. Let's talk about some words right now, proper terms that we are going to go and use. There are 3 terms that you need to be aware of. And we're going to start using them because you guys are professionals. We no longer are going to call every white wire that we come across the neutral, Right now, that's just kind of what you do in the trades. Oh, grab the neutral. There's the neutral. We're going to start calling it one of three different things. We have got either neutral conductor, we can call it, common conductor that we can call it, or identified conductor. And it really is going to go and boil down to how many lines is it actually going and balancing out. Taking a look at my panel that I have over here, I've got a 3-phase 4-wire supply. We see that we have got our buses coming down. We've got our red bus, our black bus, that's our B phase, and our blue bus, that's going to be our C phase. And then we see that we have got a neutral all the way down over here. So that's our A, B, and C phase. Inside of the panel, this would actually be referred to as the neutral bus because we see that it's able to carry back the current from all of the lines, which are also placed into that bus with it. Let's carry that out to a couple of loads. If we go and carry out to the first load over on the left over here, we see that we are going to go and have a red line, and then we've got a circuit load inside of there. We're going to have our black line coming through the breaker, circuit load over there. We're going to go and have the blue line coming through, circuit load over there. And past that, we are going to go and have where all three of these join together, we are then going to go and have the neutral. The neutral is only a thing, a real thing, any place where it is balancing current from all the other lines in the system. In a 3-phase system, that means it has to be balancing the lines of A, B, and C at the same time. We've also got another thing that is called a common conductor. A common conductor happens anytime that we have only got 2 lines that we are balancing. So if we follow this one over here, we got line A and we have got line B. We've got loads for each of those, and then past that, once those 2 tie together, we then have what's going to be referred to as a common conductor. And a common conductor carries the current that is common to both of them. It doesn't nuke the current out. We're going to find that out in a minute, but it does go and balance out some of our current. It gives us a path all the way back to the source that we need to go and have. The very last one that we are going to have is going to be my line C over here. And then I'm going to go and carry back my current with what we are then going to go and call the identified conductor. This is a word straight out of code. It's got to be identified by white, gray, longitudinal ridges, etc. off of it, but there has to be some way that we can identify what it is. Common conductor is only going to go and carry back 2 of the lines out of a 3-phase system. And common conductors only exist inside of a 3-phase system. We cannot have a common conductor inside of a single-phase system. We'll take a look at a single-phase system here in a second. But we can only have it inside of a 3-phase system. A neutral conductor can actually go and happen inside of a single-phase system or inside of a 3-phase system. And an identified conductor can happen inside of a single-phase system or inside of a 3-phase system. Let's take a look as well at a couple of our other conductors that we have up over here. We're going to go and label off some of these. This conductor over here right now, from this load all the way over up to the point where it makes connection to that, is only carrying back current from a single line. Therefore, we would go and call that one unidentified. I'm just going to put an I over there. That would be an identified conductor. Same with this one over here. From this load over to this junction would also be unidentified, and the same with this one here. From this load over to this junction would also be unidentified conductor. Let's just go and label each of these here as being identified conductors. Then, looking at this section of conductor over here, this section of conductor is currently carrying back current from the A phase as well as from the B phase. Therefore, we would call that section of conductor right over there common. And only once we hit this node over here, at that point, do we have a neutral conductor, because it's carrying back the current from all 3 of our lines altogether. Okay, that's a 3-phase setup. We're going to talk about the common conductor, the calculation in a second. I just want to go to a single-phase setup here as well. Give me 2 seconds to just erase this whole thing. And we're just going to discuss a single phase because the same terms are going to go and apply neutral and identified conductor. And we will just drag this guy off the screen. Oh, no, don't move over. Yeah, 2 seconds here. I don't have a blank screen here. Perfect, now I got a blank screen. On a single phase system, we are going to go and have our main lines coming in. We've got our line 1 and our line 2 into a panel, and then we are going to go and have a neutral inside of the panel. It's an actual true neutral because these 2 lines are 120 degrees apart. So if I come off of my panel and I wire anything out there, let's go and wire out here. We're going to take this thing from line 2 out to a load. Coming back from there, because it's only carrying current back from a single load, this line over here would just be referred to as an unidentified conductor. If I had both of my lines apparent, so I'm going to go and have my red, and I'm going to go and have my black, and then I'm going to go and have from each of them a single identified conductor that's going to come back to a node, and then past that node, I'm then going to go and have what's referred to as my neutral coming back through. This line over here would be neutral because it's carrying all of the unbalanced load. These 2 short little lines up to the junction would both be referred to as identified conductors. So it happens inside of single phase ones as well, but we don't have any place inside of here for the common. The common conductor is not going to go and be a thing inside of a single phase system. Okay, let's take a look at doing some calculations for these. Example number 3 gives us calculations for a common type of conductor. So that's where it's going only between 2 lines. If we take a look at this, we can see that we're only utilizing line A and we are utilizing line B. And the example says we got 2 line conductors and the neutral from a 122.8 volt 3-phase supply. We're supplying some single phase incandescent lighting. If the lighting is distributed with 2.5 kilowatts from line A to neutral and also 2.5 kilowatts from line B to neutral, what is the current in the common neutral conductor? So we'll just go and quickly sketch this thing out. We've got our A, we have got our B, and then we have got tying these 2 and carrying it back to our system. We are going to go and have our common over here. If we are 2.5 kilowatts and if we have got a 122.8 volt system, we know that if we're tying between a line and a neutral, therefore we must be seeing the phase value of voltage, not the line, but the phase. So if I have got a system that is a 120/208, the smaller one is always going to be the phase that I'm going to go and have. So I know that each of these has got no more than 120 volts over top of either one of those loads. So I can go and take my watts, 2,500 watts divided by 120. As soon as I go and do that, I'm going to go and end up with a current, and that current in this case is going to be 20.83 amps over here. Beautiful. 20.83 amps that I'm going to go and have through each of these together, or through each of these individually. I'm going to have 20.83 through this conductor, which is a identified conductor at this point because it hasn't joined the other. And I'm also going to go and have 20.83 through this one because it is also an identified conductor, hasn't joined. And then all of a sudden at this junction, we are now going to go and turn into a common conductor, and we're going to go and have a different value of current. Well, for us to do that value of current, we just have to place our magnitudes, 20.83 at angle 0, and this one, which is going to be 20.83 at angle 240. Let's go and pull up our calculator. We will go and add these 2 together. We're always adding when we're looking for neutrals. 20.83 angle 0 plus 20.83 angle 240 gives me a value of, would you look at that, 20.83 amps. It's the exact same. We have 2 equal currents, and those 2 currents sum up to form 1 equal current that is the exact same value, but it's at a different angle. It's at -60. It's actually lying halfway between. Taking a look at that, we see that we have got our our common current over here of 20.83 at an angle of -60, or we can call that positive 300 degrees over here. So although we've got two line values that are the same, the common carries the full value of current back with that. And this can go and change. This angle and the magnitude of this is going to be able to swing back and forth, and this is going to be able to get shorter and longer based upon what we have for differing values. If I would take some of the lights outside of here, change my kilowatts inside of here, I would once again go and change my values. Let's just do that real quick. We're going to go and say that the red line over here, my line A, is going to go and change from being 2,500. We're going to go and change that one down to 1,200. 1,200 watts, so 1,200 watts, and therefore we're going to change all of our values of current. Well, 1,200 watts divided by 120 volts is going to go and give me a value of 10 amps. So this value over here, my IA, is going to now become 10 amps at angle 0. We'll just erase this whole thing because that's all going to change. 10 at angle 0, we still have got the exact same setup on the B phase, 2,500 watts, so we're going to keep that value the same, and we'll just go and add these two together. 10 angle 0 plus 20.83 angle 240, or -120, it's up to you, you can punch either in. And we see that now our current is going to be a value between those two. It's not reaching the full value, but it's somewhere close to it. 18 that we are going to go and have, 18 amps, and it's happening at an angle of -90. And I just want to go and take a look at where that lays out on here. If it is going to be a value of 18 at -90, that means that this thing is coming down to here. We see that it has swung a little bit further out, and we've got a value now of 18 angle -90, or you could go and call that thing angle 270, whichever you prefer. It's always going to end up between, so if we've got unbalanced currents and we have got a common conductor, we are going to still end up with pretty close to our, somewhere in between those two values that's going to be carried back along there. Ultimately, whatever is delivered out to a load has to come back in, and we're proving that. This is just Kirchhoff's law of current. Whatever current enters a node has to go and return as well.